Hello everyone, today we are going to discuss some basic concepts in ecology, the idea of exponential growth in populations. This is a very fundamental idea. It has influenced the way we think about ecological populations, ecological scenarios, as well as how species evolve. So, let us try to understand what exactly do we mean by exponential growth of populations, under what conditions do we find them, and we will do this using some very basic mathematical steps. Okay. So, let me start. Okay. So, let me start with the goal of modeling populations and explicitly that of exponential or geometric growths. Okay. To do this, let us ask ourselves some very basic questions. Under what conditions do populations change over time? Let us say we know the current population, let us denote that by Nk. Nk is the current population size. You could think of Nk as population size or population density. It does not really matter very much. Okay. And what exactly is k? K is sort of an index for time, you know, it sort of you could think of it as maybe the current generation time, and we now want to ask what would be the population in a future generation. This one unit could be an arbitrary time unit, or it could be thought of as a generation. I prefer to think of it as a generation because it provides a relevant ecological time scale. Okay. So, what do you think are the processes that influence this population at a future time step? Clearly, if you were to enumerate these processes, it would depend on the current population size. There is some population that is currently present, and some of these individuals who are currently present will give rise to birth of new individuals. Let us denote that by Bk. Bk is the number of individuals who are born into this population at the kth generation. However, many of these individuals of Nk individuals also die. Let us denote that by Dk, and it is not only birth and death. For example, if I were to sort of think of this as an island where there are Nk individuals, not only do we see birth and death within this population, there could be immigration and there could be emigration out of this population. So, let us denote immigration by Ik and let us denote emigration by Ek at this generation. So, immigration increases the population size, therefore, I write plus Ik, whereas emigration reduces the population size. So, therefore, the population at a future unit time, future generation, if we take unit time as generation, would be Nk plus births minus deaths. So, these births and deaths are happening within this island, whereas the immigration and emigration are processes that are due to interaction with other islands, right. So, to make our life a little easy, what we will assume is that this is a closed population. So, if we assume a closed population, we can now say immigration and emigration are both 0. Okay. So, therefore, our equation is now simpler, the mathematical equation now becomes simpler to manage. So, we have some current population to which there are some number of births minus some number of deaths. Okay. This depicts how a population in the next generation would look like. Now, can we make further progress? Can we make some further assumptions? Before we go forward, I would like to emphasize that here I am looking at populations across generations, and I am which is sort of, I am assuming that populations are changing in some sort of steps in a discrete manner. So, which is a reasonable assumptions for many populations which have synchronous reproduction, which are strongly influenced by seasonality. Okay. Okay. So, therefore, and they are also very useful for many real world biological populations. Okay. Now, let us now make further progress to use this equation and simplify this further. Now, we now need to simplify these equations further and make sense out of them. Okay. Now, let us, what is Bk? Bk is the total number of births, right? Total births. So, what exactly is the total births? Now, imagine that if every individual on an average gives rise to small bk number of births. Let us assume that bk is the small letter b with a subscript k is the number of births that every individual on an average leads to, and the total number of births will be bk times nk. Okay. So, where bk is per capita birth rate. Okay. On the other hand, if we similarly assume that every individual has some probability of dying in a given generation, that is given by dk, the total number of deaths would be dk times nk, where dk would be per capita death rate. Okay. So, therefore, what we have now done is we are now able to express the number of individuals in a future generation is the current population size plus the per capita birth rate minus the number of individuals per capita death rate times the number of individuals, right. Now, basically if we now know the per capita birth and death rates, I can now project the population to a future generation. So, to simplify this further, I can take nk as a common factor across all the terms on the right hand side, which gives me the following equation: 1 plus bk minus dk. So, by knowing the individual level birth and death rates, we can actually now make sense of how a population in a given generation changes to a new population in the next generation. Okay. Now, see these the per capita birth and death rates, it is true that in general they are not constant. Let us now make an additional assumption to which is that bk is a constant and dk is also a constant, which I denote by b and d. If I make this assumption, then and furthermore, let us say I write r tilde is equal to b minus d. Okay. So, then we have I am sorry, I have made a small notational mistake. In the previous equation we need to have n k plus 1 Likewise here also I must write nk plus 1 because k denotes the generation number. So, we have nk plus 1 is equal to nk times 1 plus r tilde. What is this r tilde? You can sort of look at r tilde and make sense out of this. R tilde is difference between the per capita birth and death rates, and therefore, this is what we often call the growth rate. But remember one thing, so this is a growth rate defined in a discrete generational context. So, therefore, I would like to prefer to call it as geometric growth rate. So, geometric is a word to sort of distinguish a continuous time growth rate with a discrete time growth rate. So, we will discuss continuous time growth rate in future lectures. So, let us call this r tilde as the geometric growth rate, which is applicable for discrete time population models. Okay. So, now let us write this, let us also define a term called lambda, which is 1 plus r tilde, which is basically what I would call growth factor. So, many people again use lambda also to be growth rate, which I think is slightly confusing. I prefer to use the word growth factor. Some people also call lambda as finite rate of increase, but as long as we remember that we are working with populations where which are changing in sort of discrete bouts over generations, and the details within a generations are not important, we are fine. Okay. So, to summarize what we have learned so far, in discrete time population models, if we make a few assumptions such as closed population, and if we further assume that the per capita birth rate and the death rates are constant, if we make these two key assumptions, we can write the population equation in this form or in this form, where basically lambda is nothing but 1 plus r tilde, and where r tilde is the geometric growth rate, which is the difference between per capita birth and the death rates. Now, what are the implications of this? Let us now try to understand what are the implications of these equations, what can we learn further from these equations. So, let us discuss some interesting implications. Let us say, let us consider a population where n1 was the population size at the beginning, at the first generation. We now want to ask what is nk plus 1. Okay. We want to ask what is the population size going to be after k generations. Okay. Of course, we assume an intrinsic growth rate of r tilde or a growth factor of lambda. So, we now know how to calculate n2. n2 is lambda times n1, right. So, I can find out what is the population size at time 2, time at the second generation. What about n3? n3 is nothing but lambda times n2, and I am able to write this because we assume that lambda, which is a function of the per capita birth and death rates, is basically a constant. But remember that n2 itself can be written as lambda times n1 from the previous equation, right. So, therefore, n3 can be expressed in terms of n1 as lambda square times n1, right. Now, let us go further. Let us now ask what is n4, what is the population size at 4 generations. Again, we know it changes by a factor lambda, lambda times n3 is lambda n4. On the other hand, n3 is lambda square n1, right. So, I can substitute this in this equation, and therefore, we get n4 is lambda square n1. So, what do we get now? Therefore, n4 is equal to lambda times lambda square n1, which is same as lambda cube n1. Now, you can already see a pattern, okay. n2 was lambda 1 times n1, n3 was lambda 1 square n1, n4 was lambda cube n1. So, if we go on, it should not take too much effort to guess that nk plus 1 will be lambda k power n1. Right. Okay. So, now that means under the assumption of closed populations and constant per capita birth and deaths, we can actually predict what will be the population size at after an arbitrary k number of generations if we start with an arbitrary population size n1. Okay. Now, let us now further understand what does this mean, and to do this let us consider two possible scenarios. Remember what is lambda, right? Lambda was basically growth factor, and in fact recall, if just let us recall a bit, where did lambda come from? So, lambda came from the fact that nk plus 1 was lambda times nk. So, which basically means that lambda is a ratio of populations over 2 generations, which is why we called lambda as a growth factor. Okay. With that in mind, now growth factor we can think of the ratio of 2 population sizes over 2 generations as falling into 2 broad categories. Okay. First case is when this growth factor is less than 1. Okay. What does, let us, before we pursue further, let us understand what does lambda less than 1 mean. Lambda is a ratio of, look at the previous equation, lambda is a ratio of nk plus 1 to nk. Lambda less than 1 means the population is actually reduced between k and k plus 1th generation. Also remember, this means that the population reduces by a factor between generations, between consecutive generations. Okay. Let us remember one more thing, lambda was also equal to 1 plus r tilde, where r tilde itself was b minus d, right. Now, again what does lambda less than 1 mean? Lambda less than 1 means that 1 plus r tilde is less than 1, which basically means that r tilde is less than 1, less than 0, if I cancel the 2 ones, right. Now, what does r tilde less than 1 less than 0 mean? Remember that r tilde is nothing but b minus d. the per capita birth rate minus the per capita death rate. Okay, that means that B is basically less than D, which basically means on an average there are more deaths per capita, for an individual the probability of death is more than the number of offspring that individual produces, okay, which explains why r tilde was less than 0, which sort of makes sense why lambda is also less than 1, right. Okay, now with this implication, now with the understanding of all these parameter values, let us now ask what is the implication of this again. Going back to this equation now, which we had derived starting from n1, if lambda is less than 1, lambda square is also less than 1, right. Imagine take an arbitrary value for lambda, which let us say 0.5, lambda square will be 0.25, so therefore lambda square will also be less than 1, and in fact all of this will be less than 1, and in fact as you increase this exponent k, the lambda power k actually becomes smaller and smaller, becomes smaller as k increases. What does that mean? Nk plus 1 therefore is multiplied with a smaller and smaller number to n1, right, a very small number times n1, okay, and the small number becomes smaller as k increases, right. So therefore nk, if you really sort of let it go happen for a really long time, if you multiply a number with a smaller and ever decreasing number, basically that number approaches 0, okay. So what that basically means is a very intuitive thing, which is that if the number of births on an average is less than the probability of death per generation, then the population will reduce, and if it happens for every generation with the same rates, the population rapidly decreases to 0, okay, and this means that this is a case of local extinction. So lambda less than 1 or r tilde less than 0 basically causes local extinction. Now let us look at another case. So far we have now looked at the case of lambda less than 1. Now we will look at the case lambda greater than 1. Again remember that lambda greater than 1 means being a ratio of this is greater than 1, that means the populations are increasing across generations, right. Okay. And again recall that lambda is equal to 1 plus r tilde. If that is greater than 1, it is same as saying r tilde is greater than 0, right, and we know that r tilde is b minus d, that is greater than 0 means that the number of births per individual per generation are more than the probability of death of an individual per generation, okay, and which sort of explains why the populations across generations are increasing. Now what the question to ask now is basically if lambda is greater than 1, so we have this expression, if lambda is greater than 1, lambda square is greater than lambda, which lambda cube will be greater than lambda square, and in fact this number rapidly increases, okay, and rapidly increases and becomes exponentially large, geometrically large to be very precise. When we have an increase in discrete time given by lambda power k, we call them geometric population growth. Lambda k geometrically increases, okay. And this is the case of lambda greater than 1, lambda square is greater than lambda, which lambda cube will be greater than lambda square, and in fact this number rapidly increases, okay, and rapidly increases and becomes exponentially large, geometrically large to be very precise. When we have an increase in discrete time given by lambda power k, we call them geometric population growth. Lambda k And of course, we also usually call this also as an exponential growth. So that brings to the sort of the basic idea of how, starting with simple process of births and deaths, and under the assumptions of close population where we can ignore emigration and immigration, and under the assumption that the population size, the per capita birth rate and the death rates are constant, we see either an exponential decrease in the population when lambda is less than 1, which is same as birth rates are less than death rates. On the other hand, you can also have a geometrical or an exponential increase in the population size when lambda is greater than 1, which corresponds to birth rates are greater than death rates. Okay. So, now let us do a couple of graphs to understand this better. So remember again, sort of in terms of the equations, let us write down the equations that we have learned so far. Nk plus 1 is equal to lambda Nk, where lambda is the growth factor, right, and then we also learned that Nk plus 1 is lambda power k n1, okay, which basically tells that between n1 and nk plus 1 there is a geometrical increase or an exponential increase in the population. And let us also remember that the first equation can be written as the following: lambda is equal to ratio of successive population sizes, and under the assumptions of per capita birth and death rates being constant, lambda is also a constant. The ratio of the population sizes are a constant, right. Now, often in population biology we are interested in understanding how populations change. So, let us try to do that, which means what is nk plus 1 minus nk. So, we denote this as usually as delta nk. So, in mathematics the symbol delta often represents change. So, what is the change in the population at kth generation? Okay. So, what is we denote that as delta nk, but we do know from this the top equation here that nk plus 1 is lambda nk, right. So, what is delta nk? We can write this as nk plus 1 minus nk. The left hand, the first term here is lambda nk minus nk. So, what we have is lambda minus 1 times nk. Remember that lambda itself was 1 plus r tilde, right, 1 plus r tilde minus 1 times nk. Okay. So, which basically means that delta nk is nothing but r tilde times nk. So, the change in the population size at the kth generation is nothing but the per capita growth rate r tilde, right, which is b minus d times nk. Okay. Another way to write this is as follows: delta nk divided by nk, which is basically telling what was the change in the population size, and we divide this by nk. We also call this per capita growth rate. That is r tilde, which in turn is a constant by the way we have defined various quantities. Now, what I would like to do is go back here, mark these equations. Let us call this equation number 1, let us call this equation number 2, let us call this equation number 3, and then come down here and let us call this equation number 4. Let us graphically represent all of these cases. Okay. Graphical representations are often very helpful. So, let us go up and check what was okay. So, let us write down these 4 equations and we will try to now plot them. The first equation is nk plus 1 is equal to lambda nk, right. So, how would this look like in an equation? Okay, let me write this in a complete slide, new slide. Okay. So, we can write this in the following way, which is x axis is the current population size, y axis is the future population size. What is the relationship between them? Interestingly, the relationship between them is just a simple linear relationship, lambda nk. Okay, and the slope of this line is basically lambda. Okay. So, for density independent population model where lambda is constant, the relationship between nk plus 1 and nk, the 2 consecutive population sizes, would be basically a simple line. Now, let us now plot another graph which tries to connect the second equation, which tries to connect the initial population size with the kth population size. So, let k be on the x axis now, which is the generation time, and the y axis be nk. So, let us say we are starting with some at t at k is equal to 1, there is some population n1. After one generation, this becomes lambda n. Okay. After one more generation becomes lambda square. Remember that since lambda, if we assume the case of lambda greater than 1, this number increases, further. So, basically if I were to consider a very large number of generations, you would see an increasing trajectory of the population like this. Okay. That is the second way of plotting the same result. Let us now look at equation 3 and 4. Equation 3, let us again recollect what the equation 3 was. Equation 3 was basically the ratio between the 2 population sizes. Equation 4 was the per capita growth rate. Okay. Equation 3 basically so if you had population data over many generations, if you take ratio of the consecutive population sizes and plot that as a function of either k or either nk, either as a function of time or either as a function of nk, what you basically expect is a constant. Okay, if you plot the y axis, the y axis is the ratio of nk plus 1 by nk, it will be at a constant value. So, this tells that the growth factor is constant and does not change over time. So, another way to look at the same population dynamics, which is geometrical population growth, is that r tilde is equal to change in the population size divided by the current population size, right. How much change happened, and interestingly again in the case of density independent population case, this change in the population size divided by nk, which is the measure of per capita growth rate, actually would be a constant. Okay. So, what I would really like to emphasize here is that all these 4 graphs that I have shown, they are all mathematically, they all look different, but they are all mathematically equivalent. They are all capturing the fact that this is a case of discrete population dynamics, and this is a case of representing how populations are changing over time, but in different forms, and all of them convey the fact that the population grows in a density independent manner where birth rate, per capita birth rate and the per capita death rates are constants. So, with that we will stop this lecture and we will look at more complex population models in the next videos. Thank you.